The nuclear energy produced in the nuclear reaction can be put to good use, such as in the production of electricity. However, the nuclear energy can also cause much destruction, such as the explosion of a nuclear bomb. On August 6, 1945, the first atomic bomb, Little Boy, was dropped on Hiroshima. In the flash of an instant, about 66,000 people were killed and 69,000 people were injured. Introduction to Nuclear Reaction 1. In this lesson, you will learn to understand that charge and nuclear number are conserved in the nuclear reactions. Write and complete equations for nuclear reactions. Understand the principle of conservation of energy to calculate the energy released in the nuclear reaction. Understand spontaneous and non-spontaneous nuclear reactions. A nuclear reaction is a reaction involving the nucleus of an atom. Examples of nuclear reactions are nuclear decay, nuclear fission, nuclear fusion, and neutron capture. In radioactive decays, nuclei spontaneously eject alpha particles or beta particles and gamma ray and lose energy to become nuclei of lighter atoms. Click the alpha button, the beta button, the gamma button. In a nuclear fission, a heavy nucleus splits into smaller daughter nuclides. Click the nuclear fission button. In nuclear fusion, two light nuclei combine to form one heavier nucleus. Click the nuclear fusion button. In neutron capture, a neutron is absorbed by the nucleus of an atom, making the atom unstable and causing it to undergo nuclear transformation with emission of radiation. Click the neutron capture button. Some nuclear reactions occur naturally. These are termed spontaneous nuclear reactions. Spontaneous nuclear reactions are not affected by any external factors such as heat and pressure. Radioactive decay of radioisotopes of some elements is a spontaneous process. Some heavy nuclei may also undergo spontaneous fission by splitting into smaller nuclides. Non-spontaneous nuclear reactions are artificial nuclear transformations which occur when a nucleus is bombarded by a particle. The various particles used are alpha particles, protons and neutrons. The intrusion of these particles into the nucleus makes the nucleus unstable, causing it to emit radiation or splitting into smaller nuclei. Thus, non-spontaneous nuclear reactions are also called induced nuclear reactions. Summary. Examples of nuclear reactions are 1. Nuclear decays, 2. Nuclear fissions, 3. Nuclear fusions, 4. Neutron capture. Spontaneous nuclear reactions occur naturally. They are not affected by any external factors. Non-spontaneous nuclear reactions are artificial nuclear transformation produced by bombarding a nucleus with particles. Science is full of principles of conservation of mass, conservation of energy, conservation of charge, and so on. Explicitly, it means that matter can neither be created nor destroyed. In chemical reactions, the number of atoms of each kind that are present is conserved. Chemical reactions only reshuffle the atoms that were originally present into different molecular combinations. Nuclear reactions can change one kind of atom into another. Click the chemical reaction button, then the nuclear reaction button. In the nuclide notation shown above, the mass number A is also known as the nucleon number. It refers to the total number of protons and neutrons in the nucleus of an atom. The atomic number Z can also denote the charge number. Drag and drop the correct number into the brackets for the nuclide notation of proton, neutron, and electron. The nucleus of an isotope of uranium has 92 protons and 146 neutrons. What are its atomic number Z and mass number A? Answer: the atomic number Z is 92 and the mass number A is 238. In their research of radioactive decay, Rutherford and Soddy discovered that in all radioactive decays, two fundamental properties are conserved: charge and nucleon number. Later, it was found that this is true for all nuclear reactions. In alpha decay, the parent nucleus ejects an alpha particle which has 2 protons and 2 neutrons. Thus, the mass number reduces by 4 and the atomic number reduces by 2. Click the alpha decay button to see the A decay of uranium-238. Notice that the nucleon number and charge are conserved. Nucleon number 238 equals 234 plus 4. Charge 92 equals 90 plus 2. In beta decay, the parent nucleus ejects electron. Thus, it transforms into a daughter nucleus whose nucleon number is the same and the charge number increases by 1. Click the beta decay button to see the beta decay of carbon-14. Notice that the nucleon number and charge are also conserved. Nucleon number 14 equals 14 plus 0. Charge 6 equals 7 minus 1. An alpha or beta decay is often accompanied by gamma ray emission. Gamma ray emission does not change the nucleon composition of the nucleus. Summary: in nuclear reactions, 1. Nucleon number or mass number is conserved. 2. Charge number is conserved. Most nuclear reactions can be denoted by X plus X to Y plus Y, or simply X, XY, Y where X represents the particle used to bombard a target nucleus X, producing a daughter nucleus Y, and Y is the particle or radiation released in the reaction. In the above example, a copper nucleus is bombarded with a deuterium nucleus deuteron and transforms into a zinc nucleus with emission of a neutron. Notice that both nucleon number and charge are conserved. In the above nuclear reaction, an argon nucleus is bombarded by an alpha particle. It transforms into a potassium nucleus and emits a particle Y. Balance the equation by typing the correct values in the brackets. Click the answer button to check your equation. Can you identify the particle Y? Answer: Y is a proton. The above equation shows beta decay of polonium which transform into thallium. Can this nuclear reaction take place? Give your reason. Answer: no, the charge number is not conserved. Can the above reactions take place? Click on the correct answer. Summary: a nuclear reaction can be denoted by X plus X to Y plus Y, or simply X, XY, Y. When a nuclear reaction takes place, the equation for the reaction is balanced. Drag the reactants and products of the chemical reaction to either side of the scales. What do you notice? Answer: the scales is balanced. In a chemical reaction, we assume that mass is conserved. This is true as the energy released is comparatively small and the change in mass is too small to be detectable. Click the next button. Now drag the reactants and products of the nuclear reaction to either side of the scales. What do you notice? Answer: the mass of the reactants is greater than the products. In a nuclear reaction, the energy involved is so great that the change in mass is no longer negligible. One can no longer assume that mass and energy are conserved separately. Einstein explained the loss of mass or mass difference in a nuclear reaction in his famous theory on interconvertibility of mass and energy. He stated that the principles of separate conservation of mass and energy must be combined into the conservation of the total of mass and energy. Mass can be converted into energy and energy into mass by the relationship E equals mc squared. How much energy is dissipated if 1 kilogram of mass is converted to energy? Answer: E equals mc squared equals 1 times 3.0 times 10 to the power of 8 squared equals 9.0 times 10 to the power 16 joules. An average person in a developed nation uses about 5 times 10 to the power 11 joules of energy in a year. The energy dissipated by 1 kilogram of mass is sufficient to supply 180,000 person for a year. For calculation of energies involving nuclear reaction, masses of the nuclei are usually given in terms of the atomic mass unit U. Calculate the energy released during the alpha decay of uranium-238. Click through the steps to reveal the solution. Summary. In nuclear reactions, the principle of conservation of mass and energy must be combined. The energy released in a nuclear reaction can be calculated from its mass difference. Mass can be converted into energy and energy into mass by the relationship E equals mc squared.